So I debated quite a bit. It's not my first time in Zim. I've been here just a month ago, to be clear, and I'm back again. So I'm not based, I'm based in Singapore, but I'm also based in Kigali. So what happened is I go every 2 months to Kigali, and then I go back to Singapore, and go to Kigali again, and go back to Singapore. So I spent 25 years doing construction in East Africa region, not the West, the East. That would include Uganda, Tanzania, Rwanda, not really in Zimbabwe. So for the last 25 years in construction, things have actually changed quite a bit, so I do understand where things are actually going on. So I debated whether I should be talking about my favorite subject, which is called energy under resilience, or I should talk about water. And coincidentally, in the morning, seems like everybody likes to talk about water. So, good. So I'm going to carry on the topic. I was lucky enough. So I'm going to talk about how we do it in Singapore for water. It's a very interesting dialogue that we had because since 1962, when we actually separated from Malaysia, we are left alone without any resources. So we are supposed to find every other resources to actually survive and do what we need to do. So I can see people are flowing in, surely. So maybe you can start the presentation. Anyway, while they're doing the tech roundup, I might as well speak a little bit. I'm very thankful to be here, and you have a very beautiful weather compared to Singapore. We are worse off than you, to be very blunt. We are always hot, we are always humid, and there's no season, it's just one season. It just got hot and hotter. That's about all. So you're very nice, you're very blessed, you've got a nice breeze, your humidity, your precipitation are all fantastic. So, I'm going to talk about resilience, developing climate resilience architecture and infrastructure. So I'm going to speak about two things, infrastructure and architecture. Okay, quite specific on that stage. Next. So we're going to talk about water. Next. Okay, listen up. So the way my country, Singapore, has always approached resources, such as energy or water, we approach it from the soft side of things. What I mean soft approach has always been conservation and use carefully. It's always been in Singapore, conservation and use carefully. Digging it, producing more, does not solve any issues. Conservation solves issues, and usage is very important. So, soft approach brings us to what we call the 4 taps. Under the 4 taps, we have water from local catchment, imported water, new water, and desalinated water. So, I'm gonna go slow. Water from local catchment, that would mean our 17 reservoirs that we have. Imported water means the water that we import from Malaysia. I'll explain a little bit more. New water is basically black water that we actually treat and we send it back. And desalinated water, which is actually from the sea. So this is the 4. I'll give you the percentages of where we are in terms of usage, so we are 100% resilient. So out of this whole item, which you can't really see here, 1, water from local catchment are the rainwater that falls, which actually serves 2/3 of Singapore island. The whole 2/3 of island is connected to its reservoirs, which we have 17 waters. And because we collect 2/3 of our water in Singapore, the buildings are not permitted to collect any water. Anything that falls in our island belongs to our government. I repeat, anything that falls on our little island belongs to our government. So for buildings, they can, but they can only do within a certain gallons. And apart from that, they will be charged, because every resources is important in Singapore. So how it actually works in Singapore is every water that falls 2/3 of our island will get sent to either reservoirs, sent to the water treatment. That's how we do it. And then we have the imported water. So Singapore can draw up to 250 millions of gallons of water a day from Malaysia under our 1962 water agreement. So of course, around half of our current water are actually from there. And we actually built a reservoir in Malaysia to ensure that we have enough supply of water to our country. And then we have new water, which we have 5 plants, and of which 40% of our demand, we blend that particular water of new water with our reservoir water, and we pumped it back again. This is true definitely under RO process. I'm not sure whether you can see. We have an RO, reserve osmosis process, that we actually go through. Then we actually have the last one, which is desalination. We have 3 plants, and we also tell you what we're doing for the future. The future means like now and to the next 5 years. And 30%, these 3 plants of desalination serve 30% of our country needs. So that's overall about what we call our Waterloo. Coincidentally, I was talking about water. I wasn't preparing to talk about water, but since everyone was talking about water in the morning, it's quite timely to actually talk about this. Next, demand and supply. We have an issue because most of our water, right, is actually to service the non-residential, pharmaceutical. We have a lot of factories. Domestic water does not account as much compared to business or industrial water use. Hence, when I say new water, which is the non-potable water, will actually service all our industrial use. So where our water comes from? New water, which is now up to 30%, desalination, which is up to 10%, and the rest, reservoir, as well as our imported water, makes up the rest. We have a challenge in 2060 that we will require more demand for water. As such, our new water will go up by 50%, our desalination will go up by 30%, and the reservoir and imported water will be the last. Hence the ratio, as you can see, will be 80%, and we will hike it up by almost double. So from 67% now, it will go up to 90% of the land area by 2060. We will collect, out of 2/3 of our land, we will actually collect about almost all of 25 by 45 kilometers under DTS, which is Deep Tunnel Sewage Treatment, to go all the way back to our central plant. This is the compound that you actually see now, 2030 and 2060. Domestic and non-domestic use. So as a country which is thriving on commercial and economy, our pharmaceuticals and all our industrials are the biggest chunk of where our water demand is. Next. We also have a lot of greenery, I'm sure you see. Our wetlands are not exactly natural. We have what we have engineered, which we call ABC. Active, beautiful, and clean. Everything that in Singapore that we have done, all the resources are free for everyone to use. Almost everything here can be downloaded, almost everything here can be adopted by anyone that chooses. There's no copyright to this. If you go for it, it's there. So what we do for ABC is that we turn drainage into wetlands by cleverly putting gabion walls and turning into a wick stream. So in total, the driven is actually by sparkling rivers with landscape, banks, and etc. Because these are the main thing where we actually collect our waters, beside the 17 reservoirs that you actually see. So hence we have this thing called ABC water design features. You need to be trained to be ABC water design professionals. and our Public Utilities Board actually trained us to be water design professionals, where we actually learn how to curate gardens, streams in between that actually flows down. If you see this particular picture here, it's actually a school with an elevated sports stadium. Because we are so land scarce, we don't have any land, almost everything that we build is multi-purpose. The school sports is also meant for the public sports. Talking about public amenities, everything that we do, we have to share because we do not have much land to do exclusively for a purpose. So that elevated one is where this stream of water goes under. Isn't that beautiful? It's really beautiful. And that's a junior college. I'm not sure whether you're junior colleges here, that's where you study for A-levels, so that's the junior colleges for trust story. So every single stream, from the reservoirs to our housing, which is our affordable housing, which is called Housing Development Board, all has a water element that is actually built into it. Next. You like to say cost, right? So I'll tell you the cost. With such an expensive infrastructure where we actually do. It's about, in US dollars, you can see it's like 2.74. You can say it's US dollars, $2. This is about $3. That's if you want to convert it to US dollars. This is the cost of the domestic water and the cost of non-domestic water. We recently increased our water tariff only like a year and a half. We have not increased our water tariff for the last decade. So we decided to just increase because it's getting more expensive to treat it. One of the main reasons is also when we actually treat all the grey water and black water, there's a lot of phosphates in the water as well. There's a lot more cleaning, there's a lot more technology, it's more scrubbing. It's literally a circular system because our water are all potable water. Everything that comes from the tap is potable water. It goes to industry, we use what we call the new water. So we define it quite clearly. And in our potable water, once we actually say we use it for washing, it has phosphates and therefore from detergent, and that particular chemical is very difficult for us to actually clean. So as of now, we have almost banned phosphates from our washing detergents because it's going to cost us a lot. So, and therefore that goes down to the circularity about green labeling even the detergent so that we know how much phosphates actually go into detergent. We count almost every single chemical that actually goes into our water supply. Next. So, this is a video. I'm involved in this job which is called Tuas Nexus. It mixes waste as well as water. I think you have been talking about a lot of waste and water today. This project, Jacobs is a water engineer, and I'm the building engineer for that. To better tell you what's actually down here, instead of reading the diagram, I actually have a video just in case you felt sleepy after lunch because I thought that this would wake you up. So, just in case, gentlemen. I need a sound.
All the energy we can recover from waste, all the water we can reuse, and all the benefits we can derive from it.
It's about turning a vision into reality.
Singapore's water demand is rising in tandem with economic and population growth. Today, in the average household, an individual uses 141 liters of water per day. This is equivalent to 94 1.5 liter bottles. 94 really. To meet our nation's needs, one of PUB's core missions is to recycle every drop of used water.
Semakau landfill is Singapore's only landfill and it's expected to be filled up by 2035. When completed, Tuas Nexus will play an integral part in our zero waste master plan and reduce waste sent to Semakau landfill by 30% by 2030. Collectively known as TWAS Nexus, the co-location of IWMF with TWAS WRP will integrate various solid waste and used water treatment processes, harnessing various innovative synergies across the water energy waste nexus. NEA's Integrated Waste Management Facility is Singapore's first integrated facility to treat multiple waste streams.
POV's TWAS Water Reclamation Plant will be the largest membrane bioreactor facility in the world. It will enable Singapore to treat 800,000 meter cubes of used water per day. To put it simply, TWAS Nexus is greater than the sum of its parts. Synergy between waste treatment facilities and water reclamation plants is not something new. But what makes TWAS Nexus the first of its kind is that it's planned from the ground up. All efforts were coordinated to save costs and optimize land use.
We will also be expanding our circular economy approach for both solid waste and treated used water. We can now make better use of our waste as a resource. Both plants can reap more benefits within TWAS Nexus because the byproduct of one facility becomes the resource for the other.
For example, we take food waste, which will otherwise be incinerated, and mix it with used water sludge from TWAS WRP to increase biogas production. With the increased biogas, IWMF's overall thermal efficiency will be higher, and in turn, more electricity will be generated with higher carbon savings.
And part of the treated effluent from TWAS WRP, which will otherwise be discharged into the sea, goes back to IWMF for day-to-day process use.
This is truly a hand-in-hand collaboration that can only happen because we are on the same page, right from the very beginning.
What we want is climate, resource, and economic resilience. And TWAS Nexus is an integral step towards that.
When you look at TWAS Nexus on the map, we are this tiny little water droplet. When we went on site for the first time, it was amazing to see what we can achieve on this small space for the future of Singapore and to address its sustainability challenges.
This is a state-of-the-art solid waste and used water treatment facility that will definitely raise the bar for environmental and water sustainability on a global level. We can't wait for the world to finally see it.
Thank you. So that's my project. I have to go back for it. To go back to the slides. So this is the future, but it's actually under construction. So we'll finish in about 4 years time, and we have enough to meet our 2060 demand. So what we are good at is actually in planning. We plan well, and we think about it in the future in terms of resilience, in terms of if, for example, Malaysia would stop giving us water because the 1962 agreement is going to have some repercussions, at least we were able to sustain our water supply by ourselves. Next. That's for the infrastructure. I can only touch about one, water, because of 20 minutes that I have, otherwise I would touch on waste as well as energy. So I'm going to bring you next to building, which is quite an interesting topic. This may look like the what you have here, but it's not. This is actually designed by a famous architect, Hedwig. This is a school, it's actually a campus. It's just trying to tell you that you do not need glass facades when you actually design a building. You can, through your imagination, turn it into anything else. So this is actually to mimic clay, but it's not. It's actually precast concrete that was actually been designed. It's actually a very beautiful campus. It's actually a university, Nanyang Technological University. And inside is actually having a lot of daylight sessions and etc. You're most welcome to look up on videos on this and tell you a lot about it. Next. So minimizing energy demand. So again, we do not have a lot of energy. Our energy is either from oil, that we actually do it, refinery, or from the sun. And of course now only that we actually embark on hydrogen, and solar panels has always been our norm. Again, in actual fact, we cannot harvest solar because anything that falls into our land belongs to our government. so even the sun and the water, that was how it is. So, but now we are actually opening it up. So in Singapore, we have two main things. We have a lot of data centers, that's why I put data centers here, and we have very stringent guidelines for data centers. We're looking at PUE, power usage effectiveness, about 1.2. And we have this new thing that we actually coined, super low energy, which has very high efficient cooling as well as air system. We actually have the best and the best of the lots, literally, in the whole world. And we have a lot of digital integration. Everything in Singapore is actually hooked onto a smart meter. And because we have a lot of suppliers, the cost is actually quite decently cheap, I would say, for a sensor that is connected to an analog or a smart meter. Then we actually go back again. And we normally use integration, or either integration by LoRaWAN, or we actually use Sigfox, or not exactly telco. So we're very big on that. And we have best of class solar panels. So yeah, so this is one of the buildings. I just want to tell you, to tickle you on how we actually do architecture. We have what we call forest that burns from Indonesia. Not because they burn the forest, but because sometimes it's climate or whatever the reason is. And we have this thing called haze. And then that haze got swept by the wind and goes to our little island, where we normally cover with a whole blown pollution of basically forest burning. And that's not good for us. Fortunately, we suffer from that. So this design was done, won many awards when I was young. I think I was like 10 years younger. And this is designed by Toyo Ito and built by Takenaka. So what the whole idea was to actually take in fresh air from 30 stories high and pump it out into all the air system within the building. So we do not have the pollution air from the ground, we actually take out air from the sky. So that's why you have that crown looking thing, that red color thing. Is actually a wind scoop. It actually scoops the air that goes down all the way down and goes into air. Okay, I'm not sure if there's any engineers here, but there's a lot of air handling unit that actually suck it out into the building. And then we have double skin facade. We have a lot of yellow palm. We use a lot of yellow palms for outside the facade to actually purify the air as a natural purification as well. So this is one of the sky forest sections. We use a lot of simulation tools in our design, so that's to aid our design to make it better. So it's simulated and then it's verified. So we just don't use simulation design to help us with the design, but we still need to verify it. So for example, that particular wind chamber all have a sensor that we can actually monitor the amount of air intake and the quality of air that goes into our office spaces. The next one. This is by MPA. Singapore is big on MPA, which is our port authority. We have PSA, Port of Singapore Authority, as well as Maritime Port of Authority, MPA, because we are a hub for a lot of businesses. So this is, again, these are all the projects that I've done. This one is under construction. So what happened in this project was quite interesting. We have the architect, we have the engineers, we have civil structure engineer, we have mechanical electrical engineer, and we have the QS. So this is one of the projects where the CEO says that the drawing pen should not go to the architect and should have gone to the sustainability consultant. The sustainability consultant will need to set all the KPIs for your building, for your energy use and water use, and then you give the pen back to the architect, and then the architect can design whatever they want. Because then you already set a certain targets to meet, instead of giving it the pen to the architect and then they do what they think that is actually best. So sustainability targeted approach has always been an engineered approach in Singapore, which means we already know what's the savings that we want to do. So for this particular one of the things that we actually did, we did the Venturi effect, which is literally squeezing in the air from there to actually come into this particular building, which is data center. And once you actually do that, it will cool that particular facade because of the Venturi effect. And then we clad it out with a lot of building attached photovoltaic, or you can call it building integrated photovoltaic. Urban heat island, which was something that you discussed in the morning, is a norm for us to do. We always have to do urban heat island simulation. We always have to do the wind simulation, and we also have to do the wind-driven rain simulation, where you have rain and you have wind, and you need to understand how much water splashes into your corridor. And you are only allowed a certain portion of water that washes into your corridor for quality of the building. So we all of this is actually highly prescribed about to us in detail about what we need to do. So one of the design that we actually came out is what we call the illumination floor, which is the top floor, because it's all cladded. Those are not facade, those are just solar panels. So under the illumination floor is actually a big gap where a lot of lights are coming in from using of solar tubes, and you just illuminate the whole place. And of course the water feature, we actually gives a very calming effect. We always have blue and green spaces, quite a good balance within it. Next. So how we do it? We have this thing called the toolkit box of Singapore building. We address thermal performance, mainly we address diffuse radiation and radiation. The reason why we have to address diffuse radiation is because we're in tropical climate. There's a lot of heat that is coming from the outside that goes into our building. And cooling performance, we use a lot of chilled water, not just air cooling system. Wind flow, UHI, and we have loads of greenery. We actually have about 20 to 30% that is mandatory for us to conform to. And we also need to know the greenery. All of us, when we actually graduated from doing all this, we actually supposed to know all our plants, our flora and our fauna and our trees, and the PV, which is the roof as a wall, and super efficient water fittings. So our water fittings, remember when I mentioned we have the soft approach, literally almost all our fittings, water fittings, saves easily 50 to 60% of what's out there in the market in Zimbabwe as well. So not just small flush, big flush. No, we don't do that. We actually use a lot more water pressure to actually clean. So a little bit water, more pressure, and therefore use less. And this is mandated actually in Singapore for us. So super efficient water fittings. We also must do maintainability, which is smart FM, smart facility management. We must maintain our building, and maintainability is a subject. And we also have digitalization, which also we have to do, and we have our green building rating system. And as you can see, we have health and well-being, we have carbon, we have resilience as a chapter, we have maintainability also, and the last, we have intelligence. These are the 5 things that we need to do, excluding energy efficiency. This is aligned with all the UN SDG goals, which you can see down there. And so it's very much aligned with our NDC, which is National Determined Contribution of Singapore. Next. And then we have this thing called Industry Transformation Map, which is for the construction industry sector. So in here, we have collaborative contracting, which is a new engineering contract, which is called NEC4. It is to encourage mutual trust and cooperation between the contractors and the client in terms of sharing of risk and savings. And therefore, it provides a place for them to discuss so that there isn't any suspicion what the contractors want to do and what the client wants. So it's equal distribution. So this is NEC4 under project management. And then we have industry transformation map for all the cranes, crawlers, forklifts to actually use biodiesel or an antenna, which is actually a kind of solar panels that we actually put it in, and we actually use it for all our construction equipment. Next. And we have what we call the Singapore Climate Resiliency Strategy. This has been done for the last 5 years. So we have city in nature, sustainability living, and we have green economy, energy reset, as well as the resilient feature. So all of this are what we have been embarked for the last, I think, 4 years. And we're just going through another round of actually updating it so that we can actually better serve what the country wants. Next. We work as a team. So in Singapore, everyone collaborates under the Singapore Green Building Council. We have Energy Market Authority, we have Public Utilities Board, we have NEA, which is actually the waste. Everybody actually collaborates as one to come up with all the plans that we have. Thank you so much.